Thank you, Andrea. And I just wanted to start with thanking the organizers. There have been many JWST workshops, but I really like the emphasis, the unique emphasis on this one, on the synergy with ground-based telescopes. And particularly in the field of time domain astronomy and in many, many other fields, as we've heard throughout the conference, the puzzle just cannot be solved with one telescope alone. It is inherently a multi-wavelength and often a multi-messenger game. And it's really nice to see that being so actively discussed in the workshop. It's been very fun so far. So if I can change my slide. I always like to begin my talks with giving credit to students and postdocs in my group. So the top row are people at Caltech right now. The second row are people who've moved on to greener pastures. But I'll credit the contributions of this fantastic group of students and postdocs throughout this talk. So the landscape for multi-messenger astrophysics, as we've been hearing, is really rather exciting. It's completely transformed in the last 5 years, and we've seen, discovery of binary black hole mergers, the Nobel Prize winning discovery from 2015 is now routine. Every time the gravitational wave interferometers turn on, we see more black holes merging. Only a handful of neutron star mergers and very excitingly, neutron star black hole mergers are real things too. So I'll be speaking a little bit about possible electromagnetic counterparts to these gravitational wave events. We heard a beautiful talk by postdoc Robert Stein on electromagnetic counterparts to neutrinos. So I will skip that for this presentation. In terms of time domain astronomy, as I was saying at the beginning, it's inherently, again, a multi-wavelength game. And at every wavelength, just in the last few years, there's sort of an orders of magnitude improvement in sensitivity in the discovery engines itself on discovering these new types of transients in each of these different band passes. And I'm happy to report that even in the infrared, this has been one of the more challenging wavelengths to get at because the detectors are so expensive, the night sky background is so high. There are these very boring, very practical problems that had been stopping us from exploring the infrared in the dynamic universe in the infrared. But again, in just the last few years, there is progress in opening up this new window for infrared exploration, and the timing just couldn't be better with James Webb Space Telescope launch. So what I hope to convince you of today is, with these ground-based infrared discovery engines, there's a plethora of science where James Webb can actually undertake critical follow-up and solve the mystery by completing the puzzle here with ground-based discovery and space-based follow-up. So I'll give you 3 examples. Let me begin with an example close to home, which is foreground extinction by dust in the Milky Way. Here's an example of a beautiful young stellar outburst. To probe the ground-based, to overcome foreground extinction, the main thing that we need is a wide field ground-based infrared surveyor. And in the optical, thanks to advances in Moore's law and thanks to advances in cell phone technology and other things, CCDs have become very affordable. So what you see are optical imagers and how they've gotten bigger and bigger in the last few years, including one that Robert just mentioned, this Vicky transient facility at 47 square degrees. In the infrared, unfortunately, at least as of a few years ago, the biggest field of view camera was the beautiful Vista camera on the ESO telescope, but it was less than a square degree. And so how do we actually open up the infrared for exploration if we are limited in field of view? So today I'll begin with telling you about Palomar-Gattini IR, which is an infrared telescope on a teeny tiny 30 centimeter telescope, but with a very fast focal beam that has a whopping 25 square degree field of view. And what this enables is opens up the Milky Way, the galactic science for infrared time domain discovery. We mapped 15,000 square degrees every 2 nights down to about a depth of 15.7 AV mag. So this is not very far in depth. So this really limits us to the Milky Way and its immediate surrounding for discovery. But at the same time, there's just so much happening in terms of stellar science. There was a galactic fast radio burst, and this came about just when we had implemented a new readout mode with Gattini. And you can see that we could simultaneously observe at sub-second resolution this galactic fast radio burst at the same time as X-ray bursts. and say, hey, there's really nothing there, no matter how deep you look. And even if you're not impeded by extinction, it just can't be a straight line between the radio and the X-ray in terms of the inherent spectrum. Another example, and actually the brightest things in our data when we do image subtraction and look for transients, is classical novae. And here are a couple of examples of classical novae just off the galactic plane. And this I would say, ancient field where we've been discovering classical novae for literally hundreds of years now, has had a new burst of energy injected into it with these classical nova discoveries in the infrared. Because what we are finding is that just because of foreground extinction, nothing deeper than that, there are a large number of classical novae that we were missing in our census of classical novae. So if you looked at novae discovered over the past century, sort of shown in blue here, they're distributed all over the place. They're not following the mass. They're not more concentrated on the plane of the galaxy where there is most of the mass. But if you look at these handful of this novae that have been discovered just in the past couple of years with Palomar-Gattini IR, they are concentrated. They actually trace the mass. So this solves a long-standing mystery, a conundrum in the study of classical novae as to where these classical novae actually are and what are their intrinsic rates. And so we now have a robust estimation of the rate of classical novae of about 46 plus minus 13 per year. And this addresses this question of, they actually do trace the mass, and that holds together the theory of these are thermonuclear eruptions on the surfaces of white dwarfs better than a bias search, which is limited in wavelength. And there are many, many such examples that I could go into, but in the interest of time, I'll just put up one slide and give you an example of some beautiful work done by one of the organizers of this conference, Ryan Lau, on this beautiful massive star binary that you're going to hear more about. So I'm just going to put this picture up and tell you to pay attention to his talk that is coming up on his JWST ERS program on a beautiful system in our own Milky Way that he's going to decipher with James Webb very, very soon, later this year. Let me move on to a second example, a little bit further away from home. So just moving from the Milky Way to nearby galaxies. We saw this video actually in Tomek Kaminsky's talk and his discussion, lovely discussion of stellar mergers. I just want to build on that a little bit more in the extragalactic context, in the context of nearby galaxies. Tomek actually mentioned the SPIRIT survey, which was the PhD topic of my first graduate student. And Spitzer in its final years, in its final 6 years, was generous enough to give us 1,700 hours to monitor 200 galaxies over and over again in the local neighborhood. And to me, this really was, even though the field of view of Spitzer was very small, we had to target one galaxy at a time. To me, this survey actually convinced me of the potential of time domain science in the infrared. Because what it did was that, between those 6 years, between 2014 and when my student graduated in 2020, if you plot transients, infrared transients on a simple phase space where the y-axis is the intrinsic infrared luminosity and the x-axis is time scale, so phase in days, then this diagram transforms in just over the course of this survey from this picture here that you see to this, where the stars that are peppered on this diagram all over the place are the discoveries in 200 galaxies, which is a very small number by time domain standards. And it just shows how rich the infrared is for time domain exploration. And you heard from Seppo Mattia just a few minutes ago about lovely discoveries in LERGs and ULERGs. Sort of complementary to that were these discoveries that we found very obscure supernovae. We found out that actually we were missing half the supernovae in our backyard in this 30 megaparsec volume. We were missing supernovae possibly due to self-obscuration and due to this violent amount of mass loss just before explosion in our backyard. And then there's this whole class of complete first-class mysteries, which we don't have a good name for because we don't know what they are. So just for fun, we call them sprites, which are especially red intermediate luminosity transient events. And the good news is that despite the delays in James Webb launch, at least 4 targets from SPIRITS will remain bright enough for follow-up with the James Webb Space Telescope in cycle 1. And this is part of a GTO program led by Mike Ressler at JPL and designed by Ryan Lau. and a GEO program also by Ryan, which will be studying an extragalactic Wolf-Rayet outburst. Normally we think of massive stars making luminous blue variable outbursts. The word blue is in the name, except that what we were finding with SPIRITS is some really, really red massive star outbursts. We didn't have spectroscopy. There was just no way to get spectroscopy back when Spitzer was still operational because it had become warm. So James Webb will really be critical to understanding what we are seeing more like what Tomek mentioned, which was stellar mergers. Is it more in the massive star camp? Or is it these really low mass electron capture induced collapse on supernovae or something else, right? We should always keep our minds open for something else when we actually get the spectrum. So answers on this should again be coming up in just a few years. And also sort of zooming into the top right of the space, which are some of the most long-lived and most luminous supernovae. One of my collaborators, Ori Fox, has a couple of programs on James Webb as well to characterize supernovae as dust fractals, particularly these supernovae that are interacting with copious amounts of circumstellar material. And encourage you to reach out to him if you have questions about this as well. In the last part of this talk, I'd like to give you a third example that I haven't yet heard in this session yet. And that is sort of, again, a fundamental physics, a sort of nuclear physics problem, which is why the infrared is absolutely critical to overcome bound opacity. And this is, again, in the context of gravitational waves. Many of us are interested in the origin of heavy elements in the periodic table. And by heavy, I mean literally half the elements in the periodic table heavier than iron. So that's a very significant number of elements. But with these elements, just because we fill out the D shell and the F shell, the millions of line transitions translate to a very, very high bound opacity. And that's a very, very red transient. And we saw this in all its glory. This is not a theoretical concept. Five years ago, on August 17, 2017, we saw gravitational waves from two neutron star mergers, and we saw the entire electromagnetic spectrum lit up. And we saw the light curve with its hallmark signature of rapid reddening. We saw it decay like a rock in a few hours in the UV and last for a few weeks in the near infrared and a couple of months in the mid infrared. And this hallmark signature of rapid reddening could not be explained in any other way other than the production of heavy elements by our process nucleosynthesis. Here's a very nice time series of spectra taken by VLTX Shooter, just confirming that heavy elements indeed were synthesized in this binary neutron star merger. But despite this very nice data set we got from this very nearby event a few years ago, the question of whether this is a site or one of the sites or the one and only site of the production of heavy elements remains an open question. In fact, one of the things that James Webb can really do very well is answer the question of whether the heaviest of the heavy elements are produced. So if you look here, this is a solar abundance as a function of atomic mass number. There are multiple peaks in this production. And if you group them, if you just look at, say, the green elements, the lowest of the least massive of the heaviest elements, in about a month, all of that electron heating fades away. But if you look at the rest of the elements, the heaviest of the heavy elements, they dominate sort of more than a month after emission, after the merger. So if we see infrared emission beyond a month, then that is a direct clue to the synthesis of the heaviest elements. And back in 2017, when the Spitzer Space Telescope was still operational, we have these two data points, and I believe both are detections. The second one is marginal, but it's still there. But there are these two detections that Ryan beautifully did the image subtraction for. And you can see that these two detections are our only real solid clue that the heaviest of the heavy elements were in fact synthesized. And once James Webb Space Telescope is launched and we have more neutron star merger discoveries, then we can not only get photometry, but spectroscopy at this critical juncture, this critical phase, to tell us about whether, which of these heavy elements were synthesized. You can see there are a large number of elements between atomic mass number 100 and 200, right? You want to know whether it was really gold or platinum or really just neodymium or osmium that dominates the spectrum. And so spectroscopy with James Webb, the target of opportunity capability of James Webb will play a critical role in making progress on this question. So in fact, there are about 8 elements just based on those 2 data points, if you believe the theorists and their half-life calculations of all the various elements here. then there are only about 8 elements that are the most likely suspects of what is powering infrared emission nearly at 40 days and 74 days after merger. So we are predicting to see lines from these 8 elements if James Webb is able to get a spectrum of a kilonova at that late phase. Now, you may be wondering, why am I talking about this event from 5 years ago? What has happened to this field in the last 5 years? There has been a whole new third observing run of advanced LIGO. But why don't we have more kilonovae? Why don't we have kilonovae coming out of 5 years? And it turns out this is actually a much harder problem than the first one. Nature was very kind to us. We were super lucky in that first trigger to find it so easily. Since then, localizations have been much coarser, events have been much further, and there have been valiant efforts. Here I'm showing this wiki transient facility mapping thousands of square degrees to look for potential counterparts, and within minutes, within hours of merger, but not finding any, which actually suggests that probably this gravitational wave event from August 17, 2017 was not the norm. It's telling us something sort of fundamental about the luminosity function of these events. Either they're much too faint or they're just much too red. That blue emission was a gift of nature, but it's not the norm. It doesn't always happen. And what we really need is infrared discovery engines to be able to probe the corresponding emission in all cases, and not just in that 1 or 2 cases where we have the right viewing angle, the low enough lanternite fraction, the short enough remnant lifetime, and the low enough mass ratio between the 2 components. And in fact, this is particularly important with the discovery of neutron star black hole mergers, where these neutron star black hole mergers didn't even exist as a thing until 2019, when gravitational waves told us that they do exist and they are real. Because in these events, the predicted emission is again extremely red. Here I'm just showing you different examples of deep searches that were done and no counterpart was found, right? I mean, in the case of August 14th, 2019, this event was looked at, forward, backward, sideways, with optical cameras. Basically the best that was possible was done, not just by our team, but also by an independent analysis by the DES-GW team. Very, very thorough, very detailed analysis. But there was absolutely no counterpart like GW17 or 817. So that leaves us with 2 possibilities. Either it was 2 black holes to begin with, it wasn't a neutron star black hole system, or the neutron star was just swallowed whole by the black hole. And then the question is, okay, if the mass ratios are too extreme, if the black hole is really much more massive than a neutron star, then there is no electromagnetic emission to be found. But if the mass ratios are smaller, it's only a Q of say 3 or 5, not a Q of 7, then there's a lot of phase space where you expect a very red counterpart, in fact, a very luminous infrared counterpart that rapidly reddens. So how do we find this luminous, long-lived, ubiquitous infrared counterpart? Robert, in his talk, mentioned the Winter Telescope at Palomar Observatory. There's also a sister telescope at Siding Springs Observatory called DREAMS, both of which are sort of designed with the express purpose of looking for infrared counterparts to neutron star black hole mergers in the 4th observing run of LIGO Virgo, which is just coming up at the end of this year. It should begin in December of this year. And here we focus on sort of where the emission peaks, which is in the Y band, J band, and H band, and not in the I band and Z band. So we are hoping to have a better chance at finding these counterparts. Also, LIGO and Virgo interferometers are joined by the Kagra interferometer in Japan. And together, these interferometers are making great strides in improving their sensitivity, and hopefully we'll get better localized events. So hundreds of square degrees instead of thousands of square degrees for the localizations. And looking ahead, sort of a few years down the road, we want to build a dream machine in terms of infrared discovery in Antarctica, where the night sky is darker by a factor of 40 than any other mountaintop on more temperate latitudes, be it Mauna Kea or Chile or anywhere else. So some of us are exploring this concept of 100 square degree infrared surveyor dome C in Antarctica. And if anybody's interested in time domain science in frigid cold environments like Antarctica, please get in touch. And I'm happy to tell you more about this project. We do have funding now for a prototype that we're testing as we speak in the lab to retire some technology risks before we can develop the full concept here. But with all of these different projects and discovery engines that I've described, basically what I would say in the last sort of 7 years, there's been a sort of steadily growing toolkit that has been developed for ground-based, very powerful ground-based infrared discovery engines. And these infrared discovery engines will serve on a golden platter, events that are super rare, super exciting to study and characterize with the James Webb Space Telescope as a follow-up machine. And I hope we can discuss some of that in the upcoming discussion as well. What are the science opportunities here? And with that, I'd just like to thank you for your time and attention and take any questions.
Yes, thank you, Mansi, for this very nice overview talk. I have a question. Could you please expand a little bit on the potentials or limits of target of opportunity observations with James WST and coordinated observations with other facilities?
Yeah, no, that's a great question, Andrea. And my understanding is, I think currently there are 8 target of, and somebody can correct me if I misremember this, but my understanding is there are currently 8 target of opportunity observations every cycle, but with response times of only about 2 weeks or so. So nothing too disruptive, but the good news is that the infrared transients tend to evolve very slowly. So the time scale is not so bad in terms of the slowness of response. There's a lot that can be done even beyond that 2-week, where it's easier for the Space Telescope Science Institute to schedule the target of opportunity interrupts. And I think, once that delta T is longer, then there's a more unlimited number of interrupts that James Webb would be willing to approve based on what the time allocation committee thinks is the merit of the science. But I think it's that within the first 2 weeks is where there is the hardest to schedule, the most amount of effort needed from people on the ground to interrupt the queues and things like that. But thankfully, at least so far, what we've seen with the infrared is nothing fades too quickly, right? I mean, most of the infrared stuff gives us a few days, or at least a week or two is not so bad.
Yes. And in terms of coordinated observations with other facilities?
Yeah, I think that my sense is that coordinated will be more in sequel, like something on the ground discovers and then James Webb follows up. I don't know how much there will be in terms of commensal observing, right? Where at the same time as James Webb is observing, there will be other telescopes also observing. But there are sort of these opportunities for joint proposals between the X-ray and the IR, and I hope there'll be more and more of that as the cycles go along. My guess is, again, they'll be more conservative in the early years, but start to become more flexible as the cycles go.
Thanks. Mikako has a question. Fascinating talk. I would like to know some more details of heavy elements. Which lines would you expect and which wavelengths? What is the advantage of JWST over ground-based 8-meter telescopes with infrared instruments?
Yeah, and that's an excellent question. And I can tell you right now that I don't have any clue on which lines to expect. Because the problem is that all of these elements here, because in particular the ones that pulled out here, they fill the F shell, right? So there are millions of line transitions. So all these lines actually blend together. And the velocities we are talking about at the beginning is, sort of few tenths the speed of light. It does slow down in the nebular phase, but even so, the high velocities coupled with just the really large number of line transitions causes a lot of blending. So the identification of elements, specific elements, is a much trickier game. And one of the ways by which these elements can be disentangled is sort of by their half-lives and what is actually dominating the electron heating at what phase. And that's why in this paper that we wrote based on the Spitzer data points, we call out these 8 elements that are circled in red here as, if James Webb is able to get spectra and, the sort of consistent with the overall structure of lines from these 8 elements, then that is where we can make some progress in identifying the heaviest elements. And honestly, with the 8 meters, like the VLT, I mean, there's this beautiful paper led by Elena Pian, which shows spectra with X-shooter every single night. And I think this data set is about the best we can possibly do from the ground, right? Even if we have a TMT or a EELT or any of these ginormous ground-based telescopes, this is the best we'd be able to do from the ground, right? Because events would also be further away. And it's just not enough I mean, this can address the questions of some of the lighter of the heavy elements, but this beautiful, beautiful data set is not enough to address the question of the heaviest of the heavy elements, where we just need to go redder, and the atmosphere of the Earth will just not let us go any redder. So that late time nebular phase, extremely red emission is where I think James Webb will play a critical role.
Okay, thanks, Ryan.
Yeah, thanks for the nice talk, Mansi. So I had a question about, I guess, the future of these ground-based infrared surveys. So they're currently focused on near infrared, so up to maybe K-band. But I'm wondering, does it make sense to try to expand or to create ground-based surveys, transient surveys at L and M band, or is it just not worth the trade-off with sensitivity going out to those wavelengths?
Yeah, no, that's a great question, Ryan. I mean, I think, the reddest I'm daring to go in the infrared right now is with this Antarctic concept, which is in K dark at 2.35 micron. And that's because the night sky is a factor of 40 dark, specifically in the K dark bandpass in Antarctica. When you start to talk about L and M, it's really that night sky background that worries me, right? I mean, it is just the background is just so much higher that I think you could design actually an L and M band, and to be very nice for at least galactic science. But I think for extragalactic science, it would be much more challenging. But for galactic science, I think there certainly is an opportunity there to design a wide field L and M band. And there's a just by this very shallow J band survey that we did with Palomar Bettini IR, and I think there's a lot of stellar variability to uncover in our own galaxy, which we can push to with wider field L and M as well.